Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are undertaking a deep dive into the potential energy of a system of charges. It's a really key part of our discussion on electrostatic potential and capacitance. And our mission, as always, is to make this complex topic simple, clear, and absolutely exam safe for everyone. So let me start with a simple everyday question. We all know that positive charges, they repel each other.
Right, like charges repel.
So if you want to force two positive charges really close together, you have to push them very hard. My question is, where does all that energy from your pushing actually go?
It must be stored somewhere, it feels like. Like when you're stretching a rubber band.
Exactly like stretching a rubber band or compressing a spring.
So is that stored energy related to how something like lightning happens, where charges build up this, huge amount of energy before they crash?
Precisely. That's a perfect connection. This concept explains the energy in thunderstorms and even in things we use every day, like batteries. But here's a counterintuitive point, a real twist. Unlike lifting a weight, which always increases its potential energy, electrostatic potential energy can actually be negative.
Negative energy, that sounds, well, strange. If I push two, unlike charges, they attract, don't they?
They do?
So why would that result in negative energy? I'm still doing something.
That's a very genuine doubt. It's because, unlike charges, the electrostatic force is attractive. They naturally want to come together. So the external force, you're not really pushing them together. You're actually holding them back, stopping them from crashing into each other.
Oh, so I'm applying a force opposite to their movement.
Exactly. And when force and displacement are in opposite directions, the work done is negative. Or you could say the system releases energy to form these stable structures. Think of the ions in a salt crystal. They're held together by this attraction. That's a negative potential energy state.
So negative energy means stability.
Yes. It quantifies stability. It tells you how much energy you'd need to supply to break them apart again. Okay, let's unpack this. The core idea is actually quite straightforward. Electrostatic potential energy is simply the work done by an external force in assembling a system of charges by moving them from infinity to specific points against the existing electrostatic forces.
So it's the work done to build the system.
Exactly. And think of it using our primary analogy. Pushing two charges together is just like compressing a spring. The harder you squeeze, the more work you do, and the more energy is stored just waiting to snap back.
Okay, makes sense.
And the reason this whole concept exists, the why behind it, is to solve what I call the vector complexity problem.
Vector complexity. Because force is a vector, but with direction.
Yes. And adding vectors is, it can be a real headache. You have to worry about angles, components.
Yeah.
But energy is just a scalar, a number. So instead of complex vector addition, we can just add up simple numbers. It's much, much easier.
So if the repulsive energy is the potential energy, if I just let go, does that energy convert into motion? Like kinetic energy?
Yes, absolutely. Because the Coulomb force is a conservative force.
Conservative force.
Meaning the total energy, kinetic plus potential, is always conserved. Imagine the charges are connected by an invisible, taut rubber band. As you push them closer, the band stretches more and more, storing energy. If you let go,
They fly apart.
They fly apart, gaining kinetic energy and losing an equal amount of potential energy.
Right.
Now, let us see how NSERT formally defines this concept. This is really essential for your examinations.
Okay, what's the formal definition?
Could you read it out for us? The definition of potential energy of a charge at a point.
Yes, it says potential energy of charge Q at a point is the work done by the external force in bringing the charge Q from infinity to that point.
Thank you. Now, let's apply this to a system of charges using a step-by-step concept build. Imagine we are assembling three charges, Q1, Q2, and Q3 from infinity. Step 1, we bring in Q1.
Okay.
The work done, W1, is 0.
Because space is empty. There's no field to fight against yet.
Perfect. No existing field to fight. So W1 equals 0. Now, step 2. We bring in Q2. Now, Q2 has to fight the potential field that Q1 has created. Let's call it V1.
Okay, so there is work done this time.
Yes. And the work done, W2, is simply the charge, Q2, multiplied by the potential it's moving through, V1. So W2 is Q2 times V1.
Simple enough.
Now for step 3, we bring in Q3. This one has to fight the potential from Q1 and potential from Q2.
So it has to fight both V1 and V2.
Exactly. So the work done, W3, is Q3 times the sum of the potentials, V1 plus V2. The total potential energy of the whole system, U, is just the sum of all these work steps, W1 plus W2 plus W3. And when you do the maths, it simplifies beautifully to the sum of all the pair interactions.
The interaction between Q1 and Q1 and Q3 and Q2 and Q3.
Yes, that's all it is. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROSSAM.com. Now let's look at a concrete example using the formula for just 2 charges. Suppose we have Q1, which is positive, and Q2, which is negative. Let's say they are separated by 18 centimeters. Since the charges are unlike, we expect the potential energy, U, to be what?
It should be negative because they're attracting each other.
Correct. When we calculate U equals K times Q1 Q2 over R, the result in one worked example is minus 0.7 joules. The negative sign confirms the system is bound by attraction.
And that minus 0.7 joules, what does it physically mean?
It means you would have to do positive 0.7 joules of work to pull them apart again, to break the bond and separate them to infinity.
Okay, so the sign tells us whether the charges are fighting or helping each other.
Exactly. And if we connect this to the bigger picture, this whole idea of potential energy is crucial. It directly leads us to the concept of voltage, which is the foundation for understanding all of current electricity in the next unit. Now, let's eliminate some common misconceptions. These are the silent killers that often cost students marks.
Huh?
Misconception number 1. Students often think potential energy belongs only to the small test charge that is moving.
I can see why. Because we usually track the work done on that moving charge.
That's the trap.
Yeah.
But the correct idea is that potential energy belongs to the entire system of charges.
The whole system.
Yes, it's about the interaction between the charges. It's a shared property.
So it's not my potential energy. It's the potential energy of me and the source charge together. It takes 2 to have potential energy.
Very good. That's the right way to think. Misconception 2. When calculating energy for systems with 3 or more charges, students often double count the interactions.
How so?
They might count the interaction between Q1 and Q2, and then again count the interaction between Q2 and Q1.
But that's the same interaction.
It's the exact same pair. The correct idea is to use the handshake rule. In a group of people, you only count each unique handshake once.
So just count each unique pair.
Each unique pair just once. The order doesn't matter. And finally, a quick note on external fields. What if your charges are already placed in an external electric field, E?
Then there's an extra layer of interaction, isn't there?
Precisely. The total potential energy is then the sum of 2 distinct parts. Part 1 is the energy of each charge interacting with the external field. So that's Q times V external for each charge. And part 2 is the original interaction energy between the charges themselves.
The internal energy.
The internal energy.
Yeah.
You have to add both the external and the internal energies together. Here's where it gets really interesting. We need some memory hooks to make this concept stick.
Okay, I'm ready.
First, a freeze anchor. Think of potential energy as the assembly cost.
The assembly cost.
Yes, it's the cost, or maybe the profit, if it's negative, of setting up that specific arrangement of charges.
I like that. Cost to build.
Then, a mnemonic to remember the flow of concepts in this unit. Just remember, WUV.
The work done.
W gives you potential energy.
Yeah.
Which in turn helps you define potential. Or voltage, V. W leads to U, leads to V.
WUV. Got it.
And finally, a physical gesture. Try this now. Place your hands together, palm to palm.
Okay.
Now push them hard, fighting the force. That feeling of resistance, that strain in your muscles, that's stored potential energy.
I can feel it.
If you relax, your hands fly apart. That's the kinetic energy. You are literally feeling the repulsion of 2 like charges. So let's wrap up this deep dive with 3 key takeaways for your exam preparation.
Okay, the top 3 points.
Number 1, electrostatic force is conservative. This means the potential energy depends only on the final arrangement of charges, not the path you took to assemble them.
Only the final configuration matters.
Yes. Second, the potential energy of a system is calculated by summing the potential energy of every unique pair of charges. Remember the handshake rule?
Sum of all pairs, no double counting.
And third, potential energy can be positive, which means repulsion, work done against the field, Or it can be negative, which signifies attraction, a stable system where work was done by the field.
Positive for repulsion, negative for attraction.
Exactly. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
As PROF Sam.
Yes, ProfSam.com. We wish you the very best in your studies.